My name is Luciana. I'm a cyber threat intelligence analyst at State Street. Here's Brandon from our threat hunt response team. And today we're going to be talking about a shift on how malware is being delivered. DPRK, state sponsor actor, is now using blockchain infrastructure to both host and deliver malware, and that's creating very different challenges for defenders. So our goal today is to break down what we are seeing, why does that matters, and how we can prepare for a threat that doesn't behave like anything we have hunted before. So here's our agenda for today. I'm going to kick things off with what we're actually seeing in the wild, why the shift towards blockchain-based delivery malware actually matters. Then I'll walk you through the infection chain and the high level of the three techniques these actors are relying on. That's when things are going to get a bit more technical. After that, we'll look at the infrastructure behind all of this. And then Brandon is going to take over and is going to talk about why this kind of malware is so hard to shut down, the challenge this creates for hunting teams, but as well the places where detection is still possible, and then wrap things up with mitigations, recommendations, and the key takeaways. So all that said, let's move on to it. So what we're actually seeing. So we are seeing a major shift on how DPRK state sponsor actors are delivering malware. They are now leveraging blockchain to both host and distribute malware directly through smart contracts and transaction data. The payloads are normally hidden in three ways: inside the smart contracts, in transactions data, and across multiple blockchains. And those payloads aren't just simple. They are encrypted, they are heavily obfuscated, and they run entirely in memory, which make them extremely hard to detect or analyze. The focus are mainly on developers in crypto, fintech and tech, so people have access to code or infrastructure and sometimes digital assets. And then by targeting developers, the campaign can steal sensitive data, can drain cryptocurrency, and even gain long-term access to corporate environments. The motivations are DPRK motivations, like mostly financial gain through crypto theft to generate revenue and bypass sanctions, and espionage aimed at gathering intelligence to establish foothold inside tech companies. So why that actually matters? So it matters because they are now taking the very quality that makes blockchain so powerful, like decentralization, immutability, and global availability, and turn them into a hidden place for malware. That means that blockchain is no longer only a financial technology. It's now being used for delivery malware. And here's the challenges, though. None of your traditional takedowns methods apply for those kind of techniques, because there's no domains to suspend, there's no servers to seize, no VPS infrastructure to burn down. So we can't seize a smart contract. We can't delete blockchain transactions. What's on one thing is in the chain, it is there. And so there's very limited things we can do to stop it. Right now, most of the targeting are focused on individuals and DeFi platforms, but the techniques itself are fully scalable. And so what we are essentially seeing is the next generation of bulletproof hosting. With all that said, I'm going to cover a bit of the infection chain. So the attacker normally starts with classic social engineering. They normally pose as a recruiter on LinkedIn, Telegram, or Discord. They reach out to what looks like a legitimate coding test hosted normally on GitHub or NPM packages. Sometimes they even use fake video interviews or quick fix prompts to push victims into run a file. But inside those files, though, is normally they have obfuscated JavaScript loader, which once executed quietly unpacks embedded blockchain address, APIs, and keys. And that's what triggered the entire blockchain-based delivery flow. So as I mentioned, everything starts when the victim must run what looks like a legitimate JavaScript. Once the script is executed, it reaches out to a blockchain API instead of a traditional C2 server. It then pulls an encrypted payload directly from on-chain data, which blends like perfect with normal Web3 traffic. The payload then is decrypted and executed entirely in memory, so nothing ever touched the disks. From there, the malware repeats the process by pulling additional stages from the blockchain, like remote access tools, credential stealers, and wallet harvest components. And the key point here is at no stage it does rely on conventional C2 servers. Everything lives on decentralized infrastructure, giving the attack persistent, stealth, and resilience. So now we're going to move on with a brief overview of the three techniques. And again, as I said in the beginning, it's going to get a bit technical. So if you're not too familiar with blockchain, it might be a bit tricky, but just bear with us. We're going to try to show it like in a simple way. So the first technique is called ETA hiding. That's where attacker hide malicious payload inside their smart contracts. So as the image in the slide there show, the technique works by, so it starts with an initial downloader on the victim machine, which querying a malicious smart contract. In response, the contract returns the second stage payload, pulled straight from on-chain. From there, the second stage performs another blockchain lookup to fetch the third stage payload. And finally, the last payload is run entirely in memory, and you can optionally make one or more chain requests to retrieve credential stealer components. All those lookups happen through read-only calls, which generate no transactions, no logs, no on-chain trace, so nothing that would alert the defenders. And it's because smart contracts are immutable. Once malicious data is written, it can't be removed without redeploying an entire new contract, which gives the attacker a stable, persistent place to hide the code then. And on top of that, they can rotate payloads by updating contract-related values or referring new create transactions, change malware behavior without even touching the victim's machine. So here is a real example on how they rotate the payloads. In this case there, the malicious contract was updated more than 20 times, and each update cost roughly $1. $1 in gas fees, which basically the cost you pay to perform a transaction and run a smart contract on the blockchain. And because it's so cheap, the attacker can keep swapping out payloads, change configuration, and shift to where the malware is delivered. So at this point there, the smart contract stops being an ordinary code and effectively becomes a full decentralized malware host. So the next technique there is called transaction data hiding, or TX data hiding. That's even more flexible than the ETA hiding technique, because instead of storing payload inside a smart contract, the attacker hides it directly in the input data of normal blockchain transactions. The loader simply looks up for specific transactions, put the call data, and reconstruct the payload locally. So that's what makes it so effective, because it looks like exactly normal blockchain activity. In this case, there's no contract to analyze, nothing unusual is happening on the chain, and the data is stored historical, and that can never be removed. So from the defender perspective, it's branded perfectly. And from the attacker perspective, it just gives them a cheap, permanent, and extremely stealth way to host malwares. And then comes the third technique, which is the most advantage of these three techniques, most like evolution from the other two. And that's where the attackers take really full advantage of how decentralized the blockchain works. So in this technique, the attacker uses multiple blockchains together in a coordinated delivery chain. It starts with an index chain, usually Tron or Aptos, which act as the entry point. From there, the malware queries the index to obtain a reference to that point, to a transaction hash on a second chain, typically BNB smart chain. Once that reference is retrieved, then the malware pivots to BNB to pull the encrypted payload directly from the transaction data field, and then immediately decrypted it, often with simple SHOR techniques or SHOR routines. From that point, the payloads run entirely in memory, leaving almost no footprint on the disk. This multi-chain attack, though, the setup gives the attacker multi-redundancy because if the tron is blocked, they fall back to Aptos. If one RPC provider goes down, they switch to another. And even if the entire blockchain network becomes unavailable, the delivery chain keeping working. So the end result for this technique is a modular cross-platform toolkit delivered through a decentralized multi-chain infrastructure that is extremely difficult to disrupt. So here is how the cross-chain TX data hide attack looks like in real world. The initial access is simple. The victim download what looks like a normal project, sometimes shared over Telegram, sometimes shared over a GitHub repo. Once the victim runs the project, then obfuscated JavaScript is executed automatically. That script delivers two payloads. The first payload reaches across multiple blockchains to pull down a heavily obfuscated script, which has about 2,500 lines. That's nearly impossible to deobfuscate manually. But once analyzed, it turns out to be a cross-platform Node.js RAT with full remote execution capability. Once the RAT is running, then it's called back to the attack server, grabs a second stage payload, and then pull down a final payload, obfuscated JavaScript. When decrypted obfuscated Python script actually. So when decrypted that Python payload is a smash and grab toolkit, collecting browsing credentials, hook, wallets, password vaults, and anything else of value before preparing for exfiltration. So in just a few seconds, what looks like a simple GitHub repo turns out into a multi-stage cross-platform compromised with full data capability. And while sounds very complex when you look at the image, all this happened in a matter of few seconds from the moment the payloads dropped to the final stage. And so what kind of architecture is behind all this? The attacks here are not using with what we traditionally look for. There's no domains, no VPS server, no host that can be seized or blocked. Instead, everything lives on public blockchains like Ethereum, BNB, or Tron, but they don't interact with those chains directly. They go through centralized APIs providers like Aptos or Binance. So even though the payload lives on Web3, the access layer is still on Web2. And the payload in itself are stored on-chain, encrypted, with simple techniques like base64 or SHOR. And because the architecture is so modular, multi-stage, the attacker can rotate payloads or change the delivery path just by update on-chain data. So the big takeaway is that by using Web2 servers to access Web3 infrastructure, they have built a decentralized C2 model that is extremely resistant to take down. So now pass over to Brandon to talk more why it's so hard to disrupt this kind of malware techniques.
Cheers, Luciana. Thank you very much. So these are kind of really difficult from a defender perspective, but we're going to try and do our best. So why is this so hard to disrupt? Sorry, you did the slide. Yeah. So the very first thing we have is the immutability. Once things are written to the blockchain, they are there forever. They can't be deleted. Secondly, you have stealth. They use an awful lot of read-only blockchain calls and Web 2 APIs, like stated previously. The traffic looks like normal web blockchain developer activity. And unless you go and block Coinbase or block any of these people that offer the APIs, it isn't really a viable option if you work in a fintech company. The system's decentralized. There's no point of failure. They have this multi-chain redundancy across Tron, Aptos, BSC, the main Ethereum chains and others in order to go and survive disruption. Payloads are encrypted and often memory only, but sometimes there are, artifacts and metadata and things that we can find on disk, and we'll talk about that in a little bit. Attribution is incredibly difficult when dealing with these types of payloads because cryptocurrency wallets don't map to real-world identities. And when you try and run this in a sandbox, or you try test it out in a malware lab or some automated sandboxes, they usually don't pull out the full blockchain or the full payload, and this makes analysis kind of incomplete. And it can be incredibly tricky to do these multi-chain analysis steps. There is also the very low cost, 137 in gas fees to basically everyone that runs the Ethereum blockchain now hosts North Korean malware, which is incredibly cheap for them. It's cheaper than any kind of VPS or hosting provider. They can update these payloads quite quickly and quite frequently, and we have seen them do this. If they see a payload fail or they see something not working correctly, they have a very rapid development lifecycle for these things. And so our traditional detection methods, everything we're used to as blue teamers, we struggle. The infrastructure is incredibly resilient by design. And that decentralized nature is what the DPRK, what Best Korea is taking advantage of. So what is the challenge to kind of hunt for these activities from like a blue team, whether that's SOC or threat hunting activities? With traditional malware, we rely an awful lot on domains, IPs, servers, certificates, all those usual traces. With blockchain-based malware, we don't have any of that. Everything is hidden in those normal-looking blockchain traffic and RPC calls, and they blend in with regular cryptocurrency developer activity so well. And when we talk about those read-only queries, there's nearly no trace. It's post out, done, that's all you see. The payloads make things even harder, and they're encrypted or obfuscated or both. They run entirely in memory. There's very few disk artifacts. There's no signatures. And these attackers are typically using trusted platforms, GitHub, NPM, all of that stuff that developers love, and we can't reasonably block or restrict. You can't just block off an RPC endpoint or chain without breaking legitimate workflows if you do any work in cryptocurrencies. And unfortunately, you might block one chain, but because of this multi-chain nature of the more advanced payloads, this multi-chain redundancy means that if one fails, they'll just move to another. It's fine. And so disruption becomes very, very difficult. Forensics are limited. Smart contracts and transactions are immutable. And so there's nothing to take down. There's no logs. There's no DNS records. There's no registrar. There's none of those things. There's just a wallet address and the transaction hashes. And these can be tricky to act on without creating false positives, and it kind of requires a whole upskill and technical knowledge uplift for your blue teamers. Analyzing this type of malware is incredibly slow, and as previously stated, it can be quite fragile as well. Multi-chain tracing, heavy obfuscation, and blockchain calls often break in sandbox or malware lab environments. And so it can be very hard to get the full comprehensive picture of what that infection chain looked like. All of these things together, the limited visibility, the complexity, the lack of blue teamer skills in the area, and the resilient infrastructure, it creates a really perfect storm. The threat isn't really necessarily the malware. I mean, it's bad, but one of the really interesting things, or one of the biggest threats here, is the entire ecosystem, the entire environment that it works in. So when we talk about detection, I think we shouldn't get too depressed or too cynical. I mean, we do still have opportunities here, and they just look a little bit different to what we're typically used to seeing. So on the endpoint, we can watch for obfuscated JavaScript execution, in-memory payload activity if we have in-memory scanning, although that can be hit and miss, and abnormal Node.js or Python processes that just spawn unexpectedly. I hope people are watching for this kind of stuff already. These behaviors stand out even if the payload itself is obfuscated. And at a network level, we can't inspect blockchain request bodies directly. No one's doing full packet capture dumps like that. But we can spot anomalies in how these APIs are used. A sudden, multiple unusual RPC endpoints being requested. The kind of frequency analysis and unexpected frequency patterns. Or ports or things that just do not match normal developer workflows that we are used to seeing. But this requires good baseline and understanding of what is normal versus what is malicious. We can also get some early signs of socket.io based C2 initialization, suspicious ASNs, network ports, and often persistence keys is where we can catch them early, because they'll run the payload, but oftentimes they'll want to stay, particularly if it's a corporate asset where they know that they can get wider corporate access to the network, and they want to maintain that persistence, and that's a really, really, really good, strong indicator for DPRK stuff. So with all of these, metadata really is our friend here, more so than the data itself, and that's the real trick here, is the metadata and the kind of the frequency analysis. How can we kind of reduce the risk? How can we stop this? Because it's one thing to detect, but ideally we want to prevent. So at a policy level, some of the simplest wins are still the most effective. Block dangerous file types and restrict untrusted script execution wherever possible. Simple controls like that break a surprising amount of the initial infection flow. On the user or the developer side, awareness is really, really critical. These campaigns rely heavily on fake recruiters on LinkedIn and coding tasks and lead code style kind of things. Try and reinforce that simple rule. Never run unknown code from someone you don't know. Tough one, but it goes a long way if we can really drill that into people's minds. For browser security, enabling automatic updates and kind of Google Chrome's enhanced safe browsing or those similar kind of features, they break two of these DPRK kind of levers, their favorite ones anyway, like fake update prompts and malicious download lures. Again, very simple. One switch and it blocks an awful lot of this stuff right at the beginning. And for the SOC, for blue teamers, we really need to modernize our playbooks to deal with this modern threat. To start monitoring for blockchain related telemetry, even if it's just the metadata level. Invest in automated deobfuscation tooling can save an awful lot of time in the analysis stage. And just even those two capabilities will just drastically reduce that time during the IR stages and get results quicker. What are the practical steps we can take moving forward? For enterprises, the priority is expanding visibility into the Web3 ecosystem. Again, monitoring blockchain RPC patterns, tracking smart contracts and transaction hashes, building Web3 telemetry into your threat hunting workflows as well as your SOC workflows, and being proactive. Developer environments also need to be hardened because attackers are increasingly targeting the people who write and ship code. As a SOC, we need to treat blockchain as potential C2 infrastructure and prepare for this kind of decentralized malware to grow over time. That isn't the only enterprise problem. Everyday users are also being targeted, sometimes directly, sometimes indirectly, especially through fake recruiters, malicious coding tasks. So very simple habits matter. Don't run unknown code. keep your browser updated, rely on those built-in protections. Often they are surprisingly good. And only download software from trusted sources. Together, these recommendations give us a layered approach, stronger monitoring at scale, safer developer workflows, and practical guidance for individuals. It's not about eliminating the threat. We are never going to be able to do that. And we're never going to be able to stop these attackers from getting initial access and getting in. We want to make things as difficult as possible for them. We want to hamper them. We want them to start making mistakes. That's where we can catch them. So to wrap things up, before we go to Q&A, the big picture is simple. Blockchain has become a very excellent, viable, cheap C2 channel. And it fundamentally changes how malware operates. We no longer have the kind of signals that we've relied on for years and that we're used to. There is no domain to block. There is no server to take down. There are very few logs to follow. And so our detection has to shift. We're looking for behavioral and metadata level signals now. RPC usage patterns, any kind of in-memory scanning is very, very important for catching an awful lot of those JS and Python payloads. Unusual process activity, all the outliers in conjunction with blockchain activity is very, very important.
And as I mentioned before, because attackers are targeting developers directly, having those environments become critical then. And again, as Brendan mentioned, it isn't just an enterprise problem, Everyday users are being targeted through fake recruiter and malicious coding tasks. So safer habits, awareness, and hardening workflow matters for everyone. Not just for the IT teams. And finally, this isn't just a temporary trend. Decentralized malware is only going to grow. So the organizations and individuals who adapt early by implementing new telemetries and stay vigilant will be the one best in positions to defend against what is coming next. So thank you for joining us. We are happy to take any questions.
Yes, sir.
One question. Great presentation. I know very few research points towards blockchain malware. As part of the analysis journey, you have that multi-stager payloads, right? Do you envision any propagation capability in non-blockchain network as part of the malware's infection journey?
Sorry, repeat.
Yeah, so as part of how the malware propagates, do you envision any part of the multi-stage payload that affects non-blockchain network as well?
Excellent question. I'll repeat it just for the audience, and if I'm understanding correctly. So the question is, when we have these multi-chain payloads, do we envision or can we see a kind of future where some of that infrastructure would be off blockchain or would use other types of maybe decentralized networks, maybe something like IPFS, the Interplanetary File System, or things like that? I'm not the Intel guy, but I'll take a stab and answer. What we've seen from the DPRK is they are very, very, very quick to adapt new technologies for those kinds of gains. I would be very shocked if they didn't. They have some very good developers. They have some very good, and they use what works. So I think it'll fundamentally be if and when blockchain stops being as effective for them, they might use it in conjunction with another thing, like IPFS, for example. But to answer your question in a bit of a roundabout way, I would not be surprised, if that answers the question. Awesome. Silence is golden. Thank you so much, folks. You've been a great audience.